everybody, I'm Miss Cooksey, and today we're going to be talking about applying quadratic functions. So to apply quadratic functions, we're going to use all the things we've learned in the past few videos about quadratics, and we're going to look at some real life situations that involve quadratics. So one of the things that's cool about quadratic functions is that anytime there's projectile motion, so something is tossed or thrown and kind of creates an arc through the air before it lands, it can be modeled using a quadratic function. So all sports, if we throw a ball, if we throw a football, if we hit a golf ball, if we throw a water balloon, if a rocket gets shot, all of that is projectile motion, and all of that can be modeled with a quadratic. So it's one of the most real life kinds of functions that we look at in class. So we're going to look at this one situation, and we're going to solve a bunch of parts using a graph. Then we're going to go back and solve those same components using algebra. So we're going to look at a graph first, and then we're going to go back and use algebra. That way we can kind of compare the two methods. Graphing is definitely easier, but sometimes the math is messy and it's hard to read a graph, and that's where we have the algebra. So we're going to start with graphically. So, here is my situation. A water balloon is launched straight up. The balloon's flight is modeled by the function h of t equals negative 16t squared plus 192t, where h of t is the height in feet after t seconds. Answer the following questions graphically and algebraically. We're going to look at the graph first. So this is the graph of our function. H of t equals negative 16t squared plus 192t. The first question that we're going to answer is, at what height does the water balloon start? Well, if we look at our graph, the water balloon starts, the y-intercept is at 0 feet. So the water balloon starts at 0 feet. When did it reach its maximum height? Well, when the graph is at the top, that's the vertex. And the vertex happens at 6 seconds. We know that the x-axis is time because we are measuring h of t, and the y-axis is the height. So what was its maximum height? Well, at 6 seconds, its maximum height was 576 feet. When did it hit the ground? Well, it went up and it came down and hit the ground again, the other x-intercept, at 12 seconds. And the last question, looking at this graph and considering the real-world context of the problem, select the appropriate domain. So we'll remember that domain is all of the possible points from left to right. If this was just a graph without a context, we could assume that this parabola would continue to infinity in both directions and that the domain would be all real numbers. But it doesn't really make sense for a water balloon to go to a negative height. Water balloons don't bury deep underground. They hit the ground and they stop. They also don't start from negative infinity. They start from the ground. So in this case, the domain that makes the most sense is t is greater than or equal to 0 and less than or equal to 12. That's because the water balloon is really only in motion from seconds 0 to 12. While our graph has it continuing in both directions, we have to realize that the domain, the real world consequences of this graph, mean that it's probably not going to exist down here. Now we're going to solve the exact same questions, but we are going to use algebra to figure them out. So the first thing that we are going to look at is, at what height did the water balloon start? So if we want to figure out where the water balloon started, and I'm actually going to zoom in to make it a little bit easier for me to write. So at what height did the water balloon start? Well, starting is at 0 seconds. So the height when the water balloon started is the height at 0 seconds. And the height at 0 seconds would be negative 16 times 0 squared plus 192 times 0. That, when all adds up, equals 0. So the water balloon starts at 0 feet, which is the same amount of feet that we got in our graphics, or solving it graphically. Let's zoom back in again. Next, we want to figure out when will it reach its maximum height. So the maximum height is going to happen at the axis of symmetry. It's going to be the x-coordinate, because we're asking when, we're asking for the time. So when would be the time. So we want to know what is the x-coordinate when it reaches the maximum height. And we can figure that out by using our equation for the axis of symmetry, negative b over 2a. So in this case, our b is 192, so negative 192 over 2 times negative 16. You'll notice that in a lot of projectile motion questions, a is negative 16. That's because of the rate of gravity. If you're looking at questions in using the metric system, it would be negative 4.9 instead of negative 16. So negative 192 over negative 2 times negative 16 is negative 192 over negative 32, which is positive 6. So it will reach its maximum height at 6 seconds. To figure out what the maximum height was, we need to figure out where is the function at 6 seconds. So what is the height at 6 seconds? Which means h of 6 is negative 16 times 6 squared plus 192 times 6. Well, when I calculate this out, I would have negative 16 times 36 plus 192 times 6. And all of that multiplies and adds to equal 576 feet. So at the water balloon's maximum height, which happens at 6 seconds, it will be 570 feet into the air. To figure out when the water balloon hits the ground, we need to find the other x-intercept. So we need to find the x-intercepts because the x-intercepts are going to be where it's on the ground. To find the x-intercepts, we're going to set y equal to 0, and we're going to factor. So to find the x-intercepts, we have 0 equals negative 16t squared plus 192t. I'm going to go ahead and factor this. So 0 equals negative 16t times t minus 12. Now I can factor this into 0 equals negative 16t and 0 equals t minus 12. And that tells me that t equals 0 and t equals 12. So the two x-intercepts, where the line crosses the x-axis, are at 0 and 12. We know 0 is where it starts, so 12 must be when it hits the ground, so 12 seconds. The last question in this set is what was its height at 9 seconds? To figure out a height at any given number of seconds, we are just going to sub the number of seconds into our equation. Negative 16 times 9 squared plus 192 times 9. When we evaluate that, we have h of 9 equals 432. So at 9 seconds, the height is 432 feet. So to discover things, to apply quadratics in a real-world situation, we are going to use these same strategies about quadratics we've already learned. We're going to use things like finding the axis of symmetry, we're going to use things like evaluating functions, and we're going to use factoring to help find our x-intercepts. Thanks for watching. I hope this video was helpful. Make sure you subscribe if you're in my class so you never miss a video, and I'll see you next time.